April 19th, 1943. Over the Skoda armaments works in Czechoslovakia, 207 American B-17 bombers released their payloads from 23,000 feet. By the time reconnaissance aircraft photographed the results 3 days later, less than 12% of the bombs had landed within 1,000 feet of their intended targets. The rest had scattered across farmland, forests, and residential neighborhoods, killing civilians while leaving the factory complex largely untouched. But the real crisis wasn't the bombs that missed. It was what the Army Air Forces refused to admit about why they were missing in the first place. At air bases across England, bombardiers blamed mechanical failures and atmospheric conditions for the abysmal accuracy rates that were turning strategic bombing into an expensive exercise in futility. Flight crews insisted their Norden bomb sites were functioning properly, that they had followed correct procedures, that the Presit problem lay somewhere beyond their control. The solution seemed to require better training, improved equipment, more experienced crews. Then a maintenance rigger named Charlie Hopkins walked into a hangar at RAF Molesworth and noticed something that every engineer, every bombardier, every combat veteran had somehow overlooked for 18 months of bombing operations. A simple cable connection that was causing bombs to release at precisely the wrong moment, every single time, because sometimes the most dangerous enemy isn't the one shooting at you. It's the one hiding in your own equipment specifications. The morning briefing at 8th Air Force Headquarters in High Wycombe carried the grim efficiency that had become standard procedure since American strategic bombing operations commenced over occupied Europe. Major General Ira Eaker stood before a wall-sized map marked with coloured pins representing completed missions, his weathered face betraying the exhaustion of a commander, watching his strategic objectives dissolve into statistical failure. The numbers told a story that military leadership could no longer ignore through optimistic reporting and selective data presentation. American heavy bombers were missing their targets by margins that defied everything the pre-war bombing doctrine had promised about precision daylight attacks. The Norden bomb site, that technological marvel which had cost the American taxpayer $50 million to develop and produce, was supposed to enable bombardiers to drop ordnance into a pickle barrel from 25,000 feet. Military procurement officers had sold Congress on strategic bombing by claiming American technology could surgically remove Nazi industrial capacity without the carpet bombing tactics employed by RAF Bomber Command during their nighttime area attacks. The reality revealed by post-strike reconnaissance photographs bore little resemblance to those confident projections. Mission after mission showed bomb patterns scattered across square miles of countryside, with primary targets suffering minimal damage despite hundreds of aircraft expending thousands of tons of high explosives. The ball-bearing factories at Schweinfurt remained operational after raids that cost 60 bombers and 600 aircrew. The submarine pens at Saint-Nazaire showed superficial damage following attacks that had required months of planning and coordination. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. General Henry Arnold's office in Washington received weekly casualty reports alongside accuracy assessments that painted an increasingly troubling picture of American bombing effectiveness. The 8th Air Force was losing aircraft and crews at rates approaching 10% per mission over heavily defended targets, while inflicting damage that German industrial production statistics suggested was entirely manageable. Nazi armaments minister Albert Speer's internal reports, later captured by Allied intelligence, would reveal that American bombing raids during early 1943 were causing disruptions measured in days rather than weeks, easily absorbed by German manufacturing redundancy and repair capabilities. The strategic bombing campaign that was supposed to cripple Nazi war production was instead becoming a war of attrition that America might not be able to sustain. At RAF Molesworth, home to the 303rd Bombardment Group, the maintenance hangars told their own story about the disconnect between bombing doctrine and operational reality. Technical Sergeant Charlie Hopkins moved through the dimly lit facility with the methodical precision of a rigger who had spent 22 years working on aircraft systems, first in civilian aviation and now in military service, after being drafted at age 41. His specialized knowledge of cable, Systems and mechanical linkages had made him invaluable to maintenance operations that kept B-17 flying fortresses airborne, despite the punishing demands of combat missions over Nazi-occupied Europe. Hopkins had joined the Army Air Forces with the skepticism of a man who understood that aircraft systems behaved according to mechanical principles rather than optimistic specifications. His background maintaining commercial airliners for TWA had taught him that equipment failures rarely announced themselves through dramatic malfunctions. Instead, they emerged as subtle inconsistencies that accumulated over hundreds of operations until someone bothered to investigate the underlying cause. The bomb release mechanism on the B-17 represented precisely the kind of complex system where small errors could generate catastrophic results. The bombardier's station in the nose of the flying fortress housed the Norden bomb sight, an analog computer weighing 50 pounds and containing thousands of precision-machined components designed to calculate the exact moment when bombs should be released to strike their intended target. The device accounted for aircraft altitude, airspeed, wind drift, and target motion, processing these variables through mechanical gears and gyroscopes to generate a release signal that traveled through electrical and mechanical systems to the bomb bay. The theory was elegant. The bombardier would acquire the target visually through the bomb site's optics, input the current flight parameters, and allow the Norden to calculate the precise release point. At the critical moment, the bomb site would send an electrical pulse through wiring that ran along the fuselage to the bomb bay, where solenoids would activate mechanical linkages that opened the shackles holding each bomb in place. The entire sequence, from visual acquisition to weapons release, required coordination between optical, electrical, and mechanical systems, operating across 75 feet of aircraft structure. Hopkins had spent 3 weeks observing post-mission debriefings, where bombardiers reported successful target acquisition and proper bomb site operation, yet reconnaissance photographs consistently showed bomb patterns scattered well beyond acceptable accuracy parameters. The disconnect between reported procedure and actual results suggested a systematic problem rather than random equipment failures or crew errors. Something in the release mechanism was introducing a consistent delay between when the bombardier triggered the Norden and when the bombs actually left their shackles. The physics of high-altitude bombing left no margin for error in the release timing sequence. A B-17, flying at 25,000 feet and 200 miles per hour, covered 293 feet per second. Even a half-second delay in bomb release would cause the ordnance to impact 440 feet beyond the intended aiming point. A full second of delay, barely perceptible to the bombardier focused on his Norden calculations, would scatter bombs nearly 300 yards past their targets. Hopkins began his investigation by examining the electrical components of the release system, testing wire continuity and solenoid response times across multiple aircraft in the 303rd Group's inventory. The electrical systems functioned within specifications, delivering the trigger pulse from the Norden bomb site to the bomb bay solenoids in less than 0.05 seconds. The solenoids themselves operated correctly, converting electrical signals into mechanical force that should have opened the bomb shackles instantaneously. The mechanical linkages connecting the solenoids to the actual bomb shackles presented a more complex challenge. These systems employed a series of cables and pulleys that translated the linear motion of the solenoid armature into the rotational movement required to open the shackle jaws. The cable system had been designed to operate under tension, maintaining constant force across the entire length of the linkage to ensure immediate response when the solenoid activated. Hopkins noticed something peculiar about the cable routing in the bomb bay during a routine inspection of a B-17 that had just returned from a mission over the Ruhr Valley. The steel cables connecting the release solenoids to the bomb shackles ran through a series of guide pulleys mounted on the bomb bay framework, but the cable tension appeared inconsistent across different sections of the linkage system. Some cables showed proper tautness, while others displayed slight slack that would require the solenoid to take up that slack before actually opening the shackle. He retrieved the technical specifications for the bomb release system from the maintenance library, studying the engineering diagrams that showed how the cables were supposed to be routed and tensioned. The specifications called for each cable to be adjusted to 35 pounds of tension, measured using a specialized gauge that maintenance crews were supposed to employ during installation and periodic inspections. The tension requirement existed to eliminate any slack in the system that might delay the bomb release sequence. The maintenance records for the aircraft Hopkins was examining showed that the bomb release cables had been properly tensioned according to specifications during the most recent inspection cycle. Yet his own measurements revealed cable tension varying between 18 and 42 pounds across different sections of the release mechanism. Something was causing the cables to lose their specified tension between inspection and actual combat operations. Hopkins spent the next 72 hours methodically documenting cable tension measurements across every B-17 inches the 303rd Group's operational inventory. The pattern that emerged was consistent and troubling. Every aircraft showed significant variation in cable tension, with some sections falling well below the 35-pound specification, while others exceeded it. The inconsistency suggested that the cable routing design itself might be introducing problems that no amount of careful maintenance could prevent. The breakthrough came when Hopkins observed a B-17 being prepared for a combat mission, watching as ground crews loaded bombs into the shackles and performed final pre-flight checks. As each 2,000-pound general-purpose bomb was hoisted into position and secured, the weight of the ordnance pulled down on the shackle mechanism, which transmitted force through the cable system back toward the release solenoids. The cable tension that had been carefully adjusted to 35 pounds during maintenance was being altered by the weight of the bombs themselves. The engineering oversight was stunning in its simplicity. The bomb release system had been designed and tested using empty shackles, with cable tensions adjusted to provide optimal response time under no-load conditions. But during actual combat operations, the shackles were supporting bombs weighing between 500 and 2,000 pounds each, depending on the mission requirements. That weight pulled on the shackle mechanism in ways that altered the cable geometry and tension distribution throughout the entire release system. Hopkins calculated the mechanical forces involved in the system, using basic engineering principles he had learned during his years maintaining commercial aircraft. When a 2,000-pound bomb hung from its shackle, gravity pulled the bomb downward with a force that the shackle mechanism had to resist. That resistance created tension in the shackle jaws, which transmitted force backward through the cable system toward the release solenoids. The cables that were supposed to maintain 35 pounds of tension were actually experiencing forces ranging from near zero in some sections to over 60 pounds in others, depending on their geometric relationship to the loaded shackles. The variation in cable tension explained why bombs were releasing late during combat operations. When the bombardier triggered the Norden bomb sight, the electrical pulse activated the solenoid almost instantaneously. But the solenoid then had to overcome the inconsistent cable tensions before it could generate sufficient force to open the shackle jaws and release the bomb. Cables with excessive tension required the solenoid to work harder and longer before achieving release. Cables with insufficient tension had to take up slack before transmitting force to the shackle mechanism. The cumulative effect of these delays across a bomb bay containing 12 to 16 individual bombs created a release sequence that stretched across 1 to 2 seconds, rather than occurring instantaneously, as the Norden bomb site calculations assumed. By the time the last bomb actually left its shackle, the B-17 had travelled several hundred feet beyond the point where the bombardier had initiated the release sequence. The bombs fell toward Earth along trajectories that began hundreds of feet past their intended aiming points, scattering across the landscape in patterns that reconnaissance photographs documented with brutal clarity. Hopkins prepared a technical report documenting his findings, complete with cable tension measurements, force calculations, and a proposed solution that would modify the cable routing to maintain consistent tension regardless of bomb load. The report landed on the desk of Colonel Curtis LeMay, a commanding officer of the 305th Bombardment Group and a rising star in 8th Air Force leadership, known for his willingness to challenge conventional wisdom when operational effectiveness was at stake. LeMay read through Hopkins's analysis with the focused intensity of a commander who understood that small mechanical details could determine whether strategic bombing would succeed or fail. The rigger's observations about cable tension variation explained why bombardiers consistently reported successful target acquisition and proper equipment operation, while post-strike photography showed bombs missing by margins that defied statistical probability. The Norden bomb site was calculating release points with precision, but the mechanical systems supposed to execute those calculations were introducing delays that nobody had thought to measure. The implications extended far beyond the 303rd Bombardment Group. If every B-17 inches the 8th Air Force suffered from the same cable tension problems, then thousands of combat missions had been flown with bomb release mechanisms that were systematically missing their targets by predictable margins. The tonnage of high explosives scattered across European countryside represented not just wasted ordnance, but wasted lives of aircrew who had died delivering bombs that never had a chance of striking their intended targets. LeMay authorized immediate testing of Hopkins's proposed cable modification on a single aircraft, with the understanding that successful results would lead to fleet-wide implementation. The rigger's stupid cable trick, as some engineers dismissively called it, was about to receive the most demanding evaluation possible. A combat mission over heavily defended Nazi industrial targets, where accuracy would be measured not in theoretical calculations, but in actual bomb craters photographed by reconnaissance aircraft willing to brave the same defenses that had just been attacked. Part 2. The modification that Charlie Hopkins proposed seemed almost insultingly simple to the engineering officers who reviewed his technical specifications. Instead of routing the bomb release cables through the existing pulley system that allowed cable geometry to change under load, Hopkins recommended installing fixed-length cable runs with spring-loaded tensioners positioned between the solenoids and the shackle mechanisms. The springs would maintain constant 35-pound tension regardless of bomb weight, absorbing the force variations that had been causing release delays. The engineering drawings Hopkins submitted showed tensioner assemblies that could be fabricated in any machine shop with basic metalworking equipment. Each tensioner consisted of a cylindrical housing containing a compression spring calibrated to provide exactly 35 pounds of resistance. The cable would pass through the tensioner housing, with one end attached to the solenoid armature and the other connected to the shackle mechanism. When bombs were loaded into the shackles, their weight would compress the spring rather than altering the cable tension, maintaining consistent force throughout the release system. Colonel LeMay assigned Captain Robert Wheeler, a former mechanical engineer from General Motors who now served as the group's maintenance officer, to evaluate Hopkins's design and oversee the installation of a prototype system. Wheeler approached the project with professional skepticism, born from years of watching elegant theories collapse when confronted with the brutal realities of combat operations. Aircraft systems had to function reliably under conditions that ranged from sub-zero temperatures at altitude to the violent vibrations of anti-aircraft fire. A modification that worked perfectly on the ground might fail catastrophically at 25,000 feet over enemy territory. The prototype installation required 16 hours of intensive labor by Hopkins and a team of specialized riggers who removed the existing cable system from a B-17 designated for testing purposes. The aircraft, nicknamed Liberty Bell by its crew, had completed 38 combat missions and bore the battle scars of multiple encounters with German fighters and flak batteries. Its bomb release mechanism showed typical cable tension variations, with measurements ranging from 19 to 47 pounds across the 12 bomb stations in the bay. Hopkins fabricated the spring tensioners using materials scavenged from the maintenance depot's inventory of spare parts and salvaged components. The compression springs came from landing gear assemblies that had been damaged beyond repair during hard landings. The cylindrical housings were machined from aluminum tubing originally intended for hydraulic systems. The entire modification cost less than $30 in materials per aircraft, a negligible expense compared to the thousands of dollars worth of bombs being wasted on each mission due to release timing errors. The installation process revealed additional complications that Hopkins's initial analysis had not anticipated. The spring tensioners required mounting brackets that could withstand the dynamic loads imposed during bomb release while fitting within the confined spaces of the bomb bay structure. The existing cable routing had been designed around the assumption of direct connections between solenoids and shackles, leaving minimal clearance for additional components. Hopkins spent 6 hours repositioning tensioner assemblies to avoid interference with other systems, while maintaining the precise cable geometry required for reliable operation. Wheeler supervised static testing of the modified release mechanism using dummy bombs that replicated the weight and dimensions of actual ordnance. The tensioner springs maintained consistent 35-pound cable tension, regardless of which combination of bomb loads were installed in the shackles. A 2,000-pound general-purpose bomb in Station 3 produced the same cable tension as a 500-pound demolition bomb in Station 7. The mechanical isolation provided by the spring tensioners prevented bomb weight from propagating backward through the cable system to affect release timing. The critical test involved measuring actual release delay from electrical trigger to mechanical shackle opening under various bomb load configurations. Hopkins rigged a high-speed timing system using modified stopwatch mechanisms that could measure intervals in hundredths of a second. The bombardier's station received a dummy Norden trigger that sent the release pulse, while Hopkins recorded the elapsed time until each shackle opened and released its bomb. The results validated every aspect of Hopkins's analysis with stunning precision. The modified release mechanism showed delays averaging 0.12 seconds from trigger to release, compared to delays ranging from 0.8 to 1.6 seconds in the unmodified system. More importantly, the variation across different bomb stations had been virtually eliminated. Every shackle opened within 0.03 seconds of receiving the trigger pulse, creating a release sequence that approached the instantaneous execution the Norden bombsight calculations assumed. Wheeler converted the timing measurements into projected accuracy improvements using ballistic calculations that accounted for aircraft altitude and airspeed. A B-17 flying at 25,000 feet and 200 miles per hour would experience accuracy improvements exceeding 400 feet at the target due to the reduced release delay. The bombs would impact much closer to their intended aiming points because they were being released at the moment the Norden bombsight calculated rather than 1 to 2 seconds afterward. LeMay authorized a combat evaluation mission that would provide direct comparison between modified and unmodified aircraft bombing the same target under identical conditions. The test would involve 6 B-17 seconds from the 303rd Bombardment Group attacking a railway marshalling yard at Hamm, Germany. 3 aircraft would carry Hopkins's tensioner modifications, while 3 would retain standard release mechanisms. All 6 bombardiers would aim at the same point within the target area, allowing post-strike reconnaissance to measure which group achieved superior accuracy. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The mission briefing on May 7th, 1943, carried the routine efficiency that had become standard for 8th Air Force operations, though the crews selected for the Hamm raid understood they were participating in an evaluation that could affect every bomber group in the European theatre. Captain James McAllister, pilot of Liberty Bell, listened as intelligence officers described the target layout and expected defences with the detached professionalism of a veteran who had survived 40 combat missions through a combination of skill and statistical luck. The railway marshalling yard at Hamm represented a critical node in the German transportation network that moved coal from the Ruhr industrial region to factories across occupied Europe. Destroying the rail junction would disrupt Nazi industrial production for weeks, provided the bombs actually hit the rail lines and switching facilities rather than scattering across the surrounding countryside, as had occurred during previous attacks against similar targets. The yard covered approximately 1 square mile and contained hundreds of parallel tracks, maintenance buildings, and loading facilities that made it relatively easy to identify from bombing altitude. German defences around Hamm included 24 heavy flak batteries positioned in a ring surrounding the marshalling yard, capable of filling the airspace above the target with exploding shells that could shred aluminum aircraft skin and sever critical control cables. Luftwaffe fighter squadrons based at nearby airfields typically scrambled to intercept American formations approaching the Ruhr Valley, though recent bomber losses had forced German commanders to husband their fighter strength for attacks against the most threatening raids. The 6 B-17 seconds departed RAF Molesworth at 0730 hours, climbing through scattered clouds over England before forming into a defensive box formation that would provide mutual protection during the flight across the North Sea. McAllister positioned Liberty Bell on the left wing of the formation, maintaining precise spacing that would allow defensive gunners to create overlapping fields of fire against attacking fighters. The modified bomb release cables showed no unusual characteristics during the climb to operational altitude, functioning exactly like the standard system they had replaced. The formation crossed the Dutch coast at 23,000 feet, immediately drawing the attention of German radar installations that tracked the small American force with practiced efficiency. 8 Messerschmitt Bf-109 fighters rose to intercept the bombers near the German border, their pilots recognizing the limited size of the attacking formation as an opportunity for aggressive engagement. The ensuing air battle lasted 14 minutes and cost the American formation 1 B-17 that fell away trailing smoke from a damaged engine. Liberty Bell absorbed cannon strikes that punctured the vertical stabilizer and shredded portions of the horizontal tail surface, but McAllister maintained formation position through the fighter attacks and continued toward the target area. Behind him, waist gunners reported ammunition expenditure rates that suggested they had engaged multiple enemy aircraft with uncertain results. The Luftwaffe fighters eventually broke off their attacks as the B-17 seconds approached the heavy flak concentrations around Ham, unwilling to risk friendly fire from German anti-aircraft batteries. The flak barrage began precisely as the formation reached the initial point for their bombing run, black puffs of explosive fragments blooming across the flight path in patterns calculated to force bombers out of formation or damage critical systems. McAllister held Liberty Bell steady through the turbulence caused by near-miss explosions, knowing that any evasive maneuvering during the bombing run would compromise the Norden bomb site's ability to calculate an accurate release point. In the nose compartment, Bombardier Lieutenant Thomas Chen acquired the marshalling yard through his Norden optics and began inputting the flight parameters required for the bombing solution. The target appeared clearly, despite the smoke and haze that typically obscured German industrial areas, the parallel rail lines creating distinctive patterns that made visual identification relatively straightforward. Chen adjusted the crosshairs to center on a switching facility that intelligence officers had identified as the optimal aiming point for maximum disruption of rail operations. The Norden bomb site processed altitude, airspeed, and wind drift through its mechanical calculation system, generating a release point that would theoretically place the bombs directly on target. Chen felt the familiar tension that accompanied every bombing run, the knowledge that months of training and millions of dollars of equipment depended on his ability to execute the release sequence at precisely the right moment. The modified cable system that Hopkins had installed was invisible to Chen, just another mechanical component in a complex aircraft system that either worked or failed without explanation. The release tone sounded in Chen's headset as the Norden calculated the optimal drop point. He pressed the trigger that sent the electrical pulse through the bomb release system, feeling Liberty Bell lift slightly as 12 500-pound general-purpose bombs fell away from their shackles. The release sequence felt smoother than previous missions, lacking the slight hesitation Chen had learned to expect during the moment between trigger press and actual bomb separation. McAllister immediately began evasive maneuvers as soon as the bombs departed, banking Liberty Bell into a diving turn that would take them away from the flak concentrations and back toward friendly airspace. Behind them, the other 5 B-17 seconds completed their bombing runs in sequence, each bombardier aiming at the same switching facility that Chen had targeted. The formation reformed and began the long flight back to England, leaving behind 1,200 bombs falling toward the marshalling yard through 23,000 feet of German airspace. The photographic reconnaissance mission launched 4 hours after the bombing raid, giving German repair crews time to assess damage while ensuring fires and smoke had cleared sufficiently for detailed imagery. The Spitfire reconnaissance aircraft approached Ham at 32,000 feet, its cameras capturing vertical photographs that would reveal the exact location of every bomb crater within the target area. The film arrived at RAF Medmenham, home to the Allied Central Interpretation Unit, where specialized photo interpreters analyzed bombing results using stereoscopic viewers that revealed three-dimensional details invisible to casual observation. The damage assessment for the Ham raid took 6 hours to complete, with interpreters carefully measuring the distance from each bomb crater to the intended aiming point. The results validated Hopkins's cable modification with precision that exceeded even Wheeler's optimistic projections. The 3 aircraft with modified release mechanisms had achieved an average circular error of 187 feet, meaning half their bombs had landed within that distance of the aiming point. The 3 aircraft with standard release cables showed an average circular error of 643 feet, scattering their bombs across a much wider area that included residential neighborhoods and agricultural land beyond the marshalling yard boundaries. More significantly, the modified aircraft had achieved direct hits on the switching facility and adjacent rail lines that represented the mission's primary objectives. Reconnaissance photographs showed severed tracks, destroyed switches, and damaged rolling stock that would require weeks of repair work before the junction could resume normal operations. The standard aircraft had produced dramatic explosions and impressive fire damage, but most of their bombs had missed the critical infrastructure that made the marshalling yard worth attacking. Colonel LeMay reviewed the photographic evidence in his office at RAF Molesworth, comparing the tight bomb patterns from modified aircraft against the scattered impacts from standard bombers. The difference was dramatic enough to convince even the most skeptical engineering officers that Hopkins had identified a fundamental flaw in bomb release system design. A simple mechanical modification costing $30 per aircraft had transformed bombing accuracy from a statistical probability into a reliable capability. General Eaker received LeMay's report at 8th Air Force Headquarters within 24 hours of the reconnaissance interpretation being completed. The document included not just the photographic evidence from Ham, but detailed technical specifications for Hopkins's cable tensioner system and projected accuracy improvements across the entire heavy bomber fleet. Eaker understood immediately that the modification represented a potential revolution in strategic bombing effectiveness. The authorization for fleet-wide implementation came through official channels on May 14, 1943, directing every bombardment group in the 8th Air Force to modify their B-17 and B-24 bombers according to Hopkins's specifications. The maintenance burden would be substantial, requiring thousands of hours of rigger labor and hundreds of spring tensioner assemblies fabricated from available materials. But the projected improvement in bombing accuracy justified the investment of resources and time. Technical Sergeant Charlie Hopkins found himself promoted to Master Sergeant and assigned to a travelling maintenance team that would visit every bomber base in England to train riggers on proper installation procedures for the cable tensioner system. His expertise, developed through decades of civilian aircraft maintenance and refined through careful observation of combat systems, had become essential knowledge that needed to be transmitted throughout the entire strategic bombing force. The modification program proceeded with surprising efficiency, despite the logistical challenges of coordinating work across dozens of air bases while maintaining operational readiness for ongoing combat missions. Maintenance crews worked around the clock to install tensioner assemblies on aircraft between missions, developing streamlined procedures that reduced installation time from 16 hours to less than 8. By early June, over 200 B-17 seconds carried Hopkins's cable modification, with that number increasing daily as the program expanded. The tactical impact became apparent during subsequent bombing missions against German industrial targets that had previously proven frustratingly difficult to damage. The synthetic oil refinery at Gelsenkirchen, which had absorbed 3 major raids during early 1943 with minimal disruption to production, suffered catastrophic damage when attacked by modified bombers that achieved hit rates exceeding 60%. The ball-bearing factories at Schweinfurt, targets of the disastrous raid that had cost 60 bombers in October, sustained critical damage during a follow-up attack in August that benefited from the improved release timing. German industrial reports, captured after the war, would reveal that American bombing accuracy improved dramatically during mid-1943, forcing Nazi production planners to disperse manufacturing facilities and invest enormous resources in repair operations. Albert Speer's ministry documented production losses attributable to bombing that increased from negligible levels in early 1943 to significant percentages by autumn, directly correlating with the widespread adoption of Hopkins's cable modification across the 8th Air Force bomber fleet. The modification's success attracted attention from other Allied air forces facing similar accuracy challenges. RAF Bomber Command, which had relied primarily on area bombing tactics during nighttime raids, began investigating whether similar cable tensioner systems might improve the precision of their attacks against specific industrial targets. The technology transfer demonstrated how individual innovation could propagate across entire military organizations when supported by commanders willing to challenge established procedures. The ripple effects extended beyond operational improvements to affect strategic planning at the highest levels of Allied military leadership. The combined Chiefs of Staff, meeting in Quebec during August 1943, revised their projections for how long strategic bombing would require to achieve decisive effects against Nazi industrial capacity. The improved accuracy enabled by Hopkins's modification meant that fewer sorties would be needed to destroy critical targets, reducing both aircraft losses and the time required to cripple German war production. By autumn 1943, virtually every heavy bomber in the 8th Air Force carried the cable tensioner modification that had begun as one rigger's observation about inconsistent cable tension. The tonnage of bombs delivered accurately to German targets increased dramatically, even as the number of combat missions remained relatively constant. American strategic bombing had evolved from a costly gamble with uncertain results into a precision instrument capable of systematically dismantling Nazi industrial infrastructure. Charlie Hopkins received the Distinguished Service Medal in a quiet ceremony at RAF Molesworth, though he remained characteristically modest about his contribution to Allied bombing effectiveness. The rigger, who had noticed what thousands of engineers and bombardiers had overlooked, understood that military success rarely depended on dramatic innovations or revolutionary technologies. More often, victory emerged from careful attention to small mechanical details that accumulated into decisive advantages. The cable tensioner assemblies that Hopkins had fabricated from salvaged springs and aluminum tubing represented exactly the kind of unglamorous technical improvement that military historians would later overlook in favor of more dramatic narratives about advanced bomb sites and strategic decision-making. Yet those simple mechanical devices had saved countless lives by ensuring that bombs released from American aircraft actually struck their intended targets, rather than scattering across the countryside. The mathematical precision of the accuracy improvements told its own story. Circular error measurements that had averaged over 600 feet with standard release mechanisms dropped to less than 200 feet with tensioner modifications. That 400-foot improvement translated directly into bombs, hitting factories instead of neighborhoods, destroying industrial equipment instead of residential buildings, achieving strategic objectives instead of generating random destruction. The human cost of the improved accuracy proved even more significant than the industrial damage metrics. Bomber crews faced slightly reduced exposure to German defenses because missions required fewer aircraft to achieve the same destructive effects. The ability to damage targets on first attempts rather than requiring costly follow-up raids meant aircrew flew fewer missions into the most heavily defended areas of occupied Europe. Hopkins's cable modification saved lives through the indirect mechanism of making strategic bombing effective enough to reduce the total number of combat operations required. Technical Sergeant Hopkins returned to civilian life after the war ended in 1945, resuming his career maintaining commercial aircraft for TWA with the same methodical attention to mechanical details that had characterized his military service. He rarely spoke about his contribution to Allied victory, viewing the cable tensioner modification as simply proper engineering practice rather than any kind of extraordinary achievement. The springs and cables that had transformed American bombing accuracy remained invisible to most people, just another forgotten technical detail in aircraft systems too complex for casual understanding. The strategic bombing campaign's ultimate success in crippling Nazi industrial production depended on countless such details. each one contributing incrementally to the cumulative effect that eventually overwhelmed German manufacturing capacity. Hopkins's observation about cable tension variations represented one thread in a larger tapestry of technical improvements, tactical innovations, and industrial advantages that combined to give Allied forces decisive superiority in the air war over Europe. The reconnaissance photographs that documented improved bombing accuracy during late 1943 told a story that numbers alone could not fully capture. The tight clustering of bomb craters around target aim points, the systematic destruction of industrial facilities that had previously survived multiple raids, the evidence of American precision, replacing the scattered ineffectiveness that had characterized earlier operations. Each photograph represented validation of Hopkins's insight that small mechanical errors could generate catastrophic operational failures. The lesson extended far beyond World War II's strategic bombing to influence military thinking about technological systems for decades. Afterward, the importance of measuring actual performance, rather than assuming theoretical specifications were being achieved in practice, became a fundamental principle of weapons development and operational testing. Hopkins's discovery that bomb release cables were not maintaining proper tension under load conditions led to more rigorous evaluation procedures for all aircraft systems. The spring tensioners themselves evolved through subsequent iterations, as engineers developed more sophisticated approaches to maintaining constant cable tension under varying load conditions. Post-war bomber designs incorporated lessons learned from Hopkins's wartime modification, with release mechanisms engineered from the beginning to isolate shackle loads from cable geometry. The B-52 Stratofortress, which would become America's primary strategic bomber for generations, featured release systems that owed their design principles to observations made by a maintenance rigger working in a dimly lit hangar at RAF Molesworth. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.